Hola, soy Dora.
And I am Boots.
Dora, Wood, I need your help.
What's your problem?
My fridge has a bending stress problem.
But I don't know how to do this. Can you tell me more about your problem?
Axial stress and shear stress, which develop in a loaded beam, depend on the values of the bending moments and the shear forces in the beam, determining the axial stress, which is often known as the bending stress in the beam, and determining the shear stress or the horizontal shear stress. This is important because of weight. First, it would enable us to know if a particular loaded beam is being underutilized. Second, it would enable us to select the best beam for a particular load.
We will first develop a relationship for the bending stress which develops in a loaded beam. This relationship is known as the flexure formula. In this diagram, we have shown a simply supported beam loaded at the center. In this diagram, we have shown the left end section of the beam. When examining bending moment, horizontal forces act on the cross-sectional face of the beam section. We have shown only the horizontal forces along the top and bottom in the diagram at the left, but the forces act across the full cross-section as shown in the side view in diagram at the right. The horizontal forces decrease from maximum at the outer edges to zero at the neutral axis.
This sounds like an adventure.
Let's find the bridge. Let's ask for the help of the map.
I'm the map, I'm the map,
I'm the map.
we're the map, we're the map!
First,
You're going to the Arc of the Centuries.
next, you have to go to the botanical garden. Lastly, we'll go to the Lover's Lane.
Dora, where are we going?
Arch of the Centuries, Botanical Garden, and Lover's Lane. Say it with me.
Arch,
Garden,
Lover's Lane!
Could you see the arch?
Yes, that's the arch.
No! Why? Do you see something strange? It's the grumpy old crow!
Stop! Before you exit my arch, you must first learn how to derive.
We first write an expression for the bending moment produced by the horizontal forces with respect to the neutral axis, which is a line passing through the centroid of the beam cross-sectional area, which is here. So the expression for the bending moment M is simply the product of your sum of forces and your perpendicular distance to the neutral axis. We now note that we can express the force F of x as this one, that is your force acting on any small horizontal strip of area, is the product of your axial stress at that point and the amount of area. This simply comes from the definition of your axial stress, which is equal to force over area. We can now rewrite the expression for the bending moment as this one by simply substituting this equation here. We can rewrite this equation again by noting that your horizontal forces and your accompanying stresses increase linearly from 0 at your neutral axis to your maximum value at the outer edge. We can then write this equation wherein your y is your distance from the neutral axis to an area dA, and y max is your distance from the neutral axis to the outer edge of the beam cross-section. We can then write the stress at your arbitrary y as this one. And we substitute this equation here and obtain this one. Okay, so this is the equation again, and we'll notice that this is a constant, so we may factor it out of your summation term, and we'll combine your y's. We'll get a new m, which is here, factored out, and y squared. If we're going to notice, this one, your summation term, is actually your moment of inertia about the centroid of the beam cross-section. So we'll write one last time by rearranging your terms and isolating your stress term by itself, so we can obtain this equation. So that is your maximum bending stress at one location. So since your formula is derived for the maximum stress, it actually holds for the stress at any point in the beam cross-section, and it is now known as your flexure formula.
Yay! We now learn how to derive. Where are we going next, Boots?
Botanical Garden! Where are we going?
Botanical Garden! Hey! We are now at the Botanical Garden!
Let's look for Janina. Janina, can you please help us?
Sure, Dora. Sure, Boots. I have an example that could help you solve your problem. Here's the figure. In this diagram, a loaded simply supported W 10 times 45 beam is shown. For this beam, we will first determine the maximum bending moment and where it occurs in the beam. Then we will determine the maximum bending stress at that location. Step 1. Apply static equilibrium principles. First, draw the free body diagram of the structure. Then apply equilibrium conditions. From the summation of Fy is 0, we can obtain this equation number 1. Then from the equation summation of moments at B is 0, we can obtain this equation number 2. And we can also obtain the value of Rd, which is 3,500 pounds. Then we substitute this value of Rd to equation number 1 to solve for the value of Rb, which is 9,500 pounds. Step 2. Write the shear equation and the moment equation. For segment AB, shear equation is negative 5,000 pounds. The moment equation is negative 5,000x. For section BD, the shear equation is 4,500 minus 2,000 times quantity of x minus 8 pounds. And the moment equation is negative 1,000x squared plus 20,500x minus 102,000. Just substitute the values and we can obtain these values of shear and moments. For the maximum moment, we just equate VD to 0 to acquire a value of 10.5. Then substitute this 10.5 to the moment equation to obtain 3,063 pound-foot. And then just graph these computed values to obtain this shear and moment diagram.
The next step is applying the flexure formula. Using the flexure formula, stress equals M times Y divided by I, and equating it to the second or the special form of the flexure formula, M over S, and manipulating the first equation, we can derive that S equals I divided by Y. This is the formula for the section modulus. We can see from the bending moment diagram that the maximum bending moment is 20,000 foot-pounds and occurs at x equals 4 feet. We will drop the negative sign, which simply tells us that the beam is bent concave facing downward at this point. This means the top of the beam is in tension and the bottom of the beam is in compression. Now determine the value of the maximum bending stress. We already know the value of Mmax. For a 10 by 45 beam, the XX section modulus equals 49 cubic inches. Substituting the values and doing the necessary conversion, we will get the value of the maximum bending stress, we will determine the bending stress at 4 feet and 8 inches above the bottom of the beam. We have to determine y. We have to subtract the depth divided by 2 from 8, since we wish to find the bending stress 8 inches above the bottom of the beam. Y is now equal to 2.94 inches. According to the beam table, for a 10 by 45 beam, the moment of inertia of the beam is equal to 249 inches to the foot. Substituting the values and doing the necessary conversions, the bending stress will be equal to 2,830 pounds per inches square. This is a tensile stress.
Gracias, señorita.
Thank you, Janina. Thank you, May. Dora, let's now go to our next station. Lover's Lane!
Where are we going? Lover's Lane!
We are now in the Lover's Lane. And here is the bridge.
Let's solve for the bending stress.
But first, we need a calculator.
And it is inside the backpack.
Let's call backpack. Backpack.
This is the backpack. Is this the calculator?
No!
Is this the calculator?
Yay!
Let's solve for the bending stress.
In order to compute for this value, we have to know the maximum bending moment. We start off by drawing the FBD and computing for the reactions of the support.
We can now solve for our shear and moment equation. For segment AB, the shear equation is VA equals to negative 6x plus 14 kN, while for segment A to E, DVB is equal to negative 6x minus 1 kN. The moment diagram at segment AB is equal to negative 3x squared plus 14x, and for the segment AE, it is equal to the negative 3x squared minus x plus 30. Now that we have solved for the moment of inertia by using the formula VH cubed over 12, this will yield to 80 times 10 to the negative 6. We are required to solve for the bending stress at point on section B. Then, using the moment equation of the segment AD, this will yield to the moment to be equal to 9.28 kilonewton per meter. Solving for y, which is equal to the distance from the reference point, 100 minus 25 is equal to 75 millimeters. Then, substituting for the flexure formula, the negative symbolizes that the point of interest lies above the neutral axis. This will yield the moment stress to be equal to negative 8.70 megapascal. We are required to draw the stress distribution. There are following parameters that should be followed. First, the bending stress should be varying linearly with respect to the neutral axis. Then next, since the computed maximum bending stress is positive, the top half should be in compression, while the bottom half should be in tensile. Symmetry of the cross-section about the neutral axis, the maximum tensile and compressive stresses are equal in magnitude, which is 20 MPa each.
What was your favorite part of the day? I like that too. You, Boots, what's your favorite part of the day?
My favorite part of the day is this one.
My favorite part is when we learn about bending stress. Bending stress is the stress that will help us determine whether it is safe for the beam whenever load is applied. Also, it will help us determine which is the best beam to use. Here are the formulas that we have used. First is the maximum bending stress, and it is equal to the bending moment over the section modulus, which is M over S. And the second formula is the bending stress, which is equal to the bending moment times the distance from the neutral axis to any point on the cross-section of the beam over the moment of inertia, and that is My over I. And lastly is the formula for the moment of inertia I. It is equal to to base times height cube over 12. And that is BH cube over 12.